Alright, so we're going to start our last unit on quadratics here, and the whole idea behind this unit is going to involve solving equations. Now, we've solved some equations before. We spent a lot of the last couple units solving for the zeros of a quadratic, and we did it from a whole bunch of different forms. We've done it from factored form, vertex form, and from standard form. Now, to remember how we found the zeros, factored form, well, it was easy. It was already in factored form, so we set each factor to 0 when we solved. If we had it in vertex form, nice thing about vertex form is it only has one instance of x. We could set y to 0, rearrange the equation, and solve for x there. Now, with standard form, we had some options. Now, primarily, if we want to find the zeros, the best option was to see if it factored, because then once it's factored, we could put it, once we had factored form, we could get the zeros from each individual factor. Unfortunately, not everything factored. So the options that we then had at our disposal, if it didn't factor, was we had to then put it into vertex form first. So we had two ways of putting it into vertex form. We could either partially factor it and then use the symmetric points to find the axis symmetry in the vertex and create vertex form from there, or we could use the method of completing the square. And then once it's in vertex form, well, then we would know what to do. We set y equal to 0, solve for x. Eventually this unit, in a couple days, we're going to learn something called the quadratic formula, which will help us find the zeros from standard form in case something doesn't factor. We're not there yet, though, so for now, if we're in standard form and something that doesn't factor, we have to put in vertex form first. But let's do one thing at a time. Let's do some examples of all this stuff, just to remind ourselves about how we find the zeros of a quadratic. Okay, so let's start with one that's in factored form. So I want to determine the zeros of y equals bracket 5x plus 4, 7 minus 3x. Okay. Now again, you've done this before from a couple units ago. What we do is we set each factor to 0, so we wind up with two equations, 5x plus 4 equals 0, and another one over here with 7 minus 3x equals 0. And to find the zeros, we solve for x in each of these cases. So here we'll get 5x equals negative 4, or x is negative 4 over 5. Okay, and over here we are going to get 7 equals 3x, so x equals 7/3. Okay, so if you're in factored form, you're happy. You get the x-intercepts relatively quickly by solving a few relatively quick small equations. Okay, so that if you remember is how we do it from factored form. Now let's take a look at one from vertex form. Now, a common pitfall a lot of people do when you're trying to find the zeros from vertex form is they try and expand everything out and simplify and put it into standard form. Now, that actually makes things harder because in standard form you have an x squared term and an x term, and solving for x becomes a lot more difficult. In fact, in most cases you don't know how to do it yet. So the best part about vertex form, you should be happy when you see it because there's only one x in the equation. So as long as there's only one x in the equation, you should be able to solve for the variable if you need to. So remember, if you want to find the zeros, that means y equals 0 because it's the x-intercept. So if we're going to I'm going to take this equation, replace y with 0, and then solve for x. I'm going to take my equation down here, replace y with 0. Okay, so when I'm solving here, I'm isolating for x here, so I'm going to add 40 to both sides of the equation. Okay, and again, this should look familiar from last unit. We did this a few times. So we get 40 equals 4 bracket x plus 5 all squared. Okay, at this point you still cannot take the square root of both sides because of that 4 that's not squared, so we divide both sides by 4. So the left side of the equation is now 10. Okay, so now we take the square root of both sides of the equation. So we get plus or minus the square root of 10 being x plus 5. So that means that x will be equal to, once you subtract 5 from both sides of the equation, we get plus or minus root 10 minus 5 equals x. So that means we have two zeros. X equals positive root 10 minus 5, and x equals negative root 10 minus 5. Okay, and you can find the decimal equivalent for each one of these if you need to, but these are the exact values of the zeros. So even if you put it into standard form, you wouldn't be able to solve the equation explicitly because you have x squareds and x's, and we wouldn't be able to factor the equation to get factored form because there's no way you would get this through working out in an array. So this would be the way to find the zeros from vertex form. Okay, and last but not least, let's take a look at one from standard form. First thing you're going to want to try with standard form to find the zeros is you're going to want to try and put it into vertex form. Sorry, not vertex form, factored form. So you got to see if it factors first. So you have x squared plus 2x minus 15. So I'm going to try and factor it, x squared and minus 15. So you're looking for two numbers that multiply to negative 15 and add to 2. So a little bit of trial and error will tell you those two numbers are positive 5 and negative 3. So I get 5x and minus 3x. So I'm going to get x plus 5, x minus 3. Okay, so now it's factored. We're in factored form, so your zeros are going to be x equals negative 5 and positive 3. Okay, so we just took a couple examples there and reviewed how to find the zeros from standard form, factored form, and vertex form. Now let's take a look at solving. Now all those equations we looked at are trying to find the zeros, right? Now we're trying to actually, moving forward, we're going to try and solve equations that are not equal to 0, equal to something else instead. So let's think about this for a sec. So now what I'd be looking for is, instead of having a factored form equal to 0, I have factored form equal to a number. Okay, so for example, let's say I take a look at the equation y equals x plus 2 times x minus 5. Now, you could tell me the zeros of that. If I had set this whole thing equal to 0, you could find the point of intersection very easily. You'd look for the x-intercepts on the graph, and you'd see them there at negative 2 and 5. Okay, but now let's say you want this equation not to be equal to 0, but let's say you want it to be equal to something like, let's say, 8. Well, now all of a sudden you're looking for two different points of intersection. You're looking for the values of x that make the y value 8. So you got the actual answers you can see from the graph are going to be negative 3 and 6. Now, how do we actually calculate those is the question. The problem with solving this right now is we're used to solving factor form when it's equal to 0, not when it's equal to a number. Okay, similarly, we're going to be looking at vertex form when it's equal to a number and standard form when it's equal to a number. Okay, so the approach we're going to take for this one, since we know how to solve equations when they're equal to 0, we're going to try and make our equation equal to 0 in order so that we can solve. So the equation I gave you, for example, over here was x plus 2 times x minus 5. Okay, now, when we were solving it before, we had equal to 0 when we were trying to solve for the zeros. Okay, so in that situation, we're looking for the zeros. Hey, we look when x plus 2 equals 0, x equals negative 2. We look when x minus 5 equals 0, x equals 5, we get our answer. Now, all of a sudden now it's not equal to 0, it's equal to 8. So let's try and make this an equation where it's equal to 0 instead. What I'm actually going to do is subtract 8 from both sides of the equation. So if I subtract 8, now I'm going to have 0 on that side of the equation, which I liked. And I have this on this side. But now I've solved equations that are equal to 0 before, so now I can actually find my solution. If I go back to my graph over here, and now I took a look at the equation y equals x plus 2 times x minus 5 minus 8. Now, if we're looking for the zeros of that, well, now look at those points of intersection. It's negative 3, 6, the exact same x values I had that were equal to 8 in this equation up here. Okay, so by making the equation all equal to 0 and finding the zeros of that equation, then I can find the same solutions to the equation that I started with. Okay, so it seems a little abstract right now, and your head's probably spinning a little bit, but what I'm trying to look for here is I'm going to solve an equation that's not equal to 0 by solving an equivalent equation that is equal to 0. Okay, so we're going to do examples of all of these so you can actually see them in action. But in factored form, what I'm going to want is I'm going to try and have everything expanded, set equal to 0, and then try and solve it from there. If I'm in standard form and it's not equal to 0, I'm going to make it equal to 0 by bringing everything over to one side. So as a rule, your process for trying to solve any kind of quadratic equation is to get everything over on one side of the equal sign so you have 0 on the other side. If it's equal to 0, you can use the same methods of solution you've been using all along. And the only exception to this rule that I've been talking about is vertex form, because vertex form, again, is special. There's only one instance of x, so we can rearrange the equation and solve. Okay, with everything else, so you're going to want everything on one side of the equal sign, so it's equal to 0, so you can use the methods of solution you've already used in the previous couple of units. So let's take a look at some examples here. Okay, so this one's a little bit complicated, but I want to solve y equals 35, given that y is quadratic and has x-intercepts at 4/3 and -1/2, and a y-intercept at -4. So what's tricky about this one in here is, and it's a little bit tricky to start us off, is that we actually don't have an equation to start with right now. So it wants us to solve y equals 35, but we don't even know what y is. Okay, we're told it's quadratic, we're told the x-intercept and the y-intercept, but we don't have that equation. So to start, we actually have to find what our equation is. So to do that, I have to decide what form I want to start creating. Now, if I'm being given the x-intercepts, you should know from a couple of units ago, if I give you the x-intercepts, you should try and create factored form. So I'm going to have some a value I don't know. Okay, x-intercepts at 4/3 and -1/2 means I'm going to have factors of 3x minus 4 and a factor of 2x plus 1. Okay, so I've started by creating factored form. I still have to find my a value. This y-intercept is going to come in handy. I'm going to sub in that point. If it's a y-intercept, the x value is 0. So I'm going to sub in the point 0, -4. So 3 times 0 minus 4 is -4. 2 times 0 plus 1 is 1. So I get -4 equals -4a. Oh, it's a very nice a value. Happens to be 1. Okay, so this means that overall my equation is going to be y equals 3x minus 4, 2x plus 1. Okay, so all that work was just to find my equation. I still haven't actually tried to solve an equation yet, because I want to actually now set it equal to 35. I want to solve y equals 35. So I'm going to have 35 equals 3x minus 4, 2x plus 1. Okay, and first thing I'm going to do is I'm going to put this onto the graph just so we can try and visualize what the solutions are, and then we can check algebraically, see if we get the same thing. So I have 3x minus 4 times 2x plus 1. Okay, so that's my equation. Okay, and I want to set it equal to 35 and see where those points of intersection are. So if I take a look at my graph here, go up to 35, okay, you can see I'm going to have 2 points of intersection. It's going to be approximately there. I don't know why it says 35.01. It should be 35 exactly. So I have 3 and approximately -2.167 as my two answers. So I can see those from a graph. I need to be able to calculate those. So I'm going to do what I had suggested before, and that's try and bring everything over to one side of the equal sign. Before I do that, though, I'm going to expand everything out. So I'm going to leave the 35 over here for now. I'm going to expand out the 3x minus 4 times 2x plus 1 using an array. Sorry, 3x minus 4, 2x plus 1. And by now you guys are pros at expanding and simplifying with arrays. So we have 6x squared minus 8x, 3x minus 4. So you get 6x squared minus 5x minus 4. Okay, now I still haven't made the equation equal to 0. I haven't brought the 35 over yet. I'm going to do that now. So I'm going to subtract 35 from both sides of the equation. So that's going to give me 0 now on one side of the equation, and 6x squared minus 5x minus 4 minus 35 is minus 39. Okay, so with this equation right here, I'm trying to solve this. Now, I have a quadratic equals 0 now, so this equation right now, I'm actually looking for the x-intercepts. Well, how do I find the x-intercepts of something in standard form? I try to factor it. So hopefully this factors, because if not, it's a much, much longer process. So I'm going to put in 6x squared and minus 39. I'm going to leave it to you guys to factor this. So take a few seconds and factor this and push play and you're ready to see the answer. Okay, so when I factor this, I got 6x plus 13 times x minus 3. So that gives me my factored form here. And from there, I'm done. So well, not quite done. I still have to solve for x. So from each factor, I set equal to 0. So when I have x minus 3 equals 0, I wind up with x equals 3. And when I get 6x plus 13 equals 0, I get x equals negative 13 over 6. Okay, so we'll just quickly finish this up in part 2, and we'll see you over there.